is we are mostly focusing on RAG. Uh, in simple terms, we all know it's retrieval augmented generation. So the retrieval part, in case we want to integrate in the workflow is, imagine we have like 5,000 paragraphs. We can't dump in the LLMs because it could be, it goes beyond the context window. It has a lot of information noise, so it can't. There's possible chances of not able to find the right information based on the query we are interested. The higher the input, the higher the cost. So OpenAI not only charges on output token, but it also charges on the input. So if you're only interested in one paragraph out of 5,000, why waste money and also time? Because the higher the input information, the longer it takes to generate the output. So it makes sense to use right retrieval for the right query and answer it. So that's the basic workflow where, let's say we have a PDF containing your birth date. LLM out of the box might not have your information of that. So we first retrieve that information from the right text or PDF file you upload, and then we ask LLM, okay, use this information and append and augment and answer the question using the information fetched from the PDF rather than your past knowledge. So uh, when you hear discussions of LLM hallucination in RAG, there are basically two areas where it could hallucinate. Either it was unable to retrieve the right paragraph to answer for the user query. So that's why in the WhatsApp group, there was discussion about, okay, RAG accuracy is more dependent on the right retrieval, better retrieval approaches rather than the generation part. And second is parsing. And what I mean by that is we are retrieving text information to answer the query. You have information in various formats like PDF, PPT, Excel, CSV, you name it. So how do we convert that information into the right text part to answer? And I'll tell, that's where in as we move ahead, we are using embedding to find the similarity. in in simple terms, for example, if we have 5,000 paragraphs and I have a query, what is the right structure wall thickness? So the basically what embedding does is, for 5,000 paragraphs, we're going to create around 1,000 dimension vector. So each 5,000 paragraph has a vector. And then for our query related to structural wall thickness, we're going to create another vector. And in simple terms, we're going to find cosine similarity out of this 5,000 paragraph. What are the top 3 paragraphs which are similar? Then we just find the score, use those top 3 paragraphs. Uh, from vector, we get back to the original text, which of the top 3 results, append it to the user query and say, generate the answer. So uh, there are opportunities of failure in this part, because how do you break the text makes a big difference, because all this embedding does is, okay, if the semantic meaning is more like man, king, they are in one cluster, woman, but there is no absolute value. So let's say I am interested in what are the pros of healthy diet, and in my text, if I make a paragraph which has both pros and con, so there's a possibility when you do paragraph embedding, it has a neutral meaning. But if you do the same content as 2 separate paragraphs, like pros as one paragraph, cons as a, and then while doing cosine similarity in embedding, you will retrieve the right pro related paragraph and answer it. So uh, basic words, chunking makes a big difference in making RAG application accurate. So we'll go in detail later, but embedding, parsing, chunking makes a big difference in making RAG applications reliable. Uh, any questions before we start? Amazing. Let's do. So basically, there is a closed source approach where in this script, we're going to use OpenAI, but also we can develop the same application using open source models, where we need open source embedding and open source LLM. So for that, if we need GPU, but for closed source, we don't need GPU because we're going to use hosted OpenAI embedding and hosted OpenAI LLMs for that. So let's just get the basic document. So you can make a copy in your respective drive folder. I, I have this basic 4-page PDF of Californian building code, and but first we'll go through like basic example of a huge essay text of Polygram and how embedding and RAG application would work. So this is Google Colab, and it's pretty easy to use. Uses Python language, and we are using Google's compute for this exercise. So basically, if you have a URL which you want to test, you just replace it here. And if you click on this folder, you'll see the downloaded data. So I was just using it before, so it's reconnecting. Mm, I'll just use CPU. Meanwhile, I'll share other information. So unstructured, like llama parse, is another library for getting unstructured to structured data. And as I was saying, how important chunking is for the application. This is a really good blog. I'll share it in the chat as well if you want to follow along. But the basic ideas are: do you do sentence wise splitting? Do you do like paragraph wise splitting? Uh, or if you have like, let's say 10 sentences, do you overlap uh, the last sentence in first and second chunk? Uh, so if you have large PDF, do you do PDF wise chunking, or do you do like uh, similarity? So this is a good blog if you want to check out what are the various chunking. Huh, why am I? Sorry, I'll just restart my collab. Meanwhile, we would need like OpenAI key. So I can quickly share how you would get it. So if you go to platform.openai.docs in your profile, click on this icon and create user API keys, and we'll just create one. All right, so maybe I'll just use my another account. This, let's see. All right, let's now paste it up. So here I'm just downloading a building code section. This I'm downloading Polygram's essay. So installing Llama index library because we are going to use some of the utils. The way like the older version had all the like LLMs as part of the original library, with the newer version they have decoupled it, so you don't install all the integrations as part of the core library. So um, okay, right. And we'll do login, and the OpenAI key we generated, gonna use it here. So with getPass, it's just a secure way you can use. So paste it, press enter, and we're gonna. So the way Llama index we work for the RAG application is you can define your LLM, and we have to pass that LLM in the basic settings uh, and OpenAI embedding as part of, because the workflow involves both. So here, simple, gonna create an instance of both. And so this is a great util from Llama index. Whatever files you have it in your folder, uh, you can refresh this if it's not showing. First, you can fetch all the content and load that content, and then the thing which I didn't mention earlier is we are creating those embeddings, and this is one of the session in Google Colab. Once you close it, you're going to lose all those embeddings. That's the reason there are like vector database storage like Pinecone and others. Llama index, this with this function, we can store the embedding in the memory. With this extra things we can see, it created 22 embeddings. So so in short, 22 paragraphs, 22 vectors for the new query. We're gonna find the most common similarity. So basic, there's a query. Oops, I think I didn't run this. All right, so your query query engine. Here's how you pass new queries, and here's the output. Now, how do we know whether this was generated from the LLM memory or past data, or this was generated using the data we passed? So you could find, like, this is how people make citations and other thing in their apps, where uh, we can find what were the two closest nodes, like, for this query with the cosine similarity and embedding. Then we use this information to answer this query. And if you want to see the whole text information, this is just another util where this was the answer. So retrieval LLM augmented that and answered those questions based on the original query. That's that's the RAG part. So this is how, for various queries, you can find the closest content in your whole unstructured data in your firms. So regarding the point I mentioned, that okay, storing those embeddings, and how does those embeddings look like? This is another function. Uh, okay, so here's the storing embedding function. So you could see, like, since we're creating this for the first time, uh, technically we already have index defined above, so we just need to use this last line. But just for the sake of simplicity, we are creating all the vector embeddings, and then we're storing it locally. So the next time we want to reuse the app, we can save some money on creating embeddings and just load it from locally rather than, or you could store it in Pinecone like database as well and retrieve it. So I think this is just gonna test. And once you run this, we'll see a storage folder here. And we can, if you click on the default vector store, for here you'll get, here's how a vector looks like. And these are the embeddings. So once you have this embedding, we have the corresponding text paragraph. So that's how we can use those embeddings in future. And if you want to, like, make a app which you can share with your colleagues, or make a SaaS app, like, the easiest way I've done using, like, Gradio. So you're just packaging these things. Gonna use the same workflow, define embedding and LLM models, create the whole, like, embedding database, instantiate it. And for the input, we're gonna take, I think we'll just see soon. So the way Gradio works is like, okay, we're gonna take the user input, these are the two expected output, and on submit, process this function. So I'm just, like, simplifying, like, what are the retrieval nodes, and this giving those citations in the app. So same interest. So here we will see LLM generated answer. And if we want to see what was the source from the original essay index, we have here source one, and this was the whole information used, and metadata information source two. So here's how we can create a very simple basic RAG app. Any questions?
Hey, Mayur. Thanks for that. And some questions on the embedding side. I, like, long time ago, worked with, like, the earlier versions of the LSTM and I guess the skipgram and stuff. And there used to be this whole world of, like, how to do embedding. So in terms of that, do you think, like, there are different ways, or how do you improve your embeddings, or what works?
Yeah, so great question. So I think the way I'll do it is, right now you saw for this query, we got this to retrieval based on our embedding. The way we could improve embedding is by benchmarking across various embeddings. So Cohere has its own embedding, there are open source embedding and OpenAI embeddings. So at the end of this code doc, I am also showing a open source embedding. So this is from Hugging Face, and we are defining the bundle, and we can create the same embedding data. So the metric I would monitor is that for a given query, I'll have, like, let's say 3 to 5 embedders, monitor the top 2 or top 3 retrieve nodes. Then I can evaluate which embedding was able to find the right paragraph and which was not. And maybe for that use case, then go ahead with that embedded model.
Okay. Yeah, that makes sense. And then I guess, sorry, a follow-up question. You said like you're giving like in terms of the number of dimensions for the vector space. I think you mentioned one for each paragraph. Is that what you're using here?
Yeah, like so here I'm just using a default setting, but I have like a small snippet here where, for example, this code, we
Yep.
can take the input uh, text data, and then I can define chunk size of 1024. So basically, these are the tokens, and like
All right.
if and I can then have a overlap size, and then when I define these nodes, this is like first node, and it took like around, you can see 1,000 words based on the tokenizer.
Yeah.
It will get those chunk. So there are various ways, sentence wise, title wise, paragraph wise. So that's another, like, chunking and parsing and embedding. Those are the three benchmarking efforts one should do to improve the reg model accuracy.
All right. Yeah, that makes sense.
Yeah,
Yeah, I think my experience like was to like tokenize each single word, which obviously would be a lot of large space of embeddings. Yeah.
yeah. You're always making a trade-off. Like, let's say you have 5,000 uh, words. If you tokenize each, then you're looking for a long cosine similarity. Long, like,
Yeah.
the embedding cost will be so high because for each token you're, let's say, paying microcents, but
Yeah.
each word, even one word will create also 1,000 dimension vector, and 1,000 word paragraph will also create the same vector. So but each vector creation is going to cost you money. So what's a good trade-off of right information chunking, right uh, chunk size? So
Yeah. Thank you.
yeah.